All right, ladies and gentlemen, welcome to today's math class. And what we're going to do today is we're going to conclude our discussion on direct variation. And what I did was I actually wrote down here in your textbook, or excuse me, here on my whiteboard, the last two examples of the section that are found in your textbooks on page 108. And what we're going to see in this class is pretty much a two-story problems or more of a real world application of direct variation. So let's look at this example right here. It says hailstone. It's an example that's talking to us about hailstone formations. Okay. So the problem reads, hailstorms form when strong updrafts support ice particles high in clouds, where water droplets freeze onto the particles. The diagram shows a hailstone at two different times during its formation. A. Write an equation that gives the hailstone's diameter d after t minutes if you assume that the diameter varies directly with time. And B says use your equation from part A to predict the diameter of a hailstorm after 20 minutes. So it talks about a diagram. So let's draw that diagram. And if you go to your book on page 108 and you look at that example, specifically the one with the hailstones, you have a diagram to about that at the right of the page, and it says basically a diameter, assuming that a hailstone is a circle. A diameter is a line that passes through an imaginary line that passes from one point or part of a circle to another, and it has to pass through the center. And if you look at the first diagram, all it says is D, and they give you a question mark, pretty much a question mark. The only thing that you're being given is the time, which is 20 minutes, but you're not being given a diameter. And in the second diagram, which is at the bottom or below this one, you have another hailstone formation. Again, a perfect circle, unlike this one. You have a diameter, which is an imaginary line that passes from one area of a circle to another, passing through the center. And they're saying here that the diameter is 12. And remember that they want us to give them the units in inches, so 12 inches. I'm sorry, 0.75 inches, excuse me. 0.75 inches. And the time is 12. I apologize. So this time is in minutes here. A hailstone of 12 inches would be crazy, but actually it's the time. Time is 12 minutes, and the diameter is 0.75 inches. So time is 12 minutes. And this one is also minutes here. Let me finish that abbreviation real quick. Okay, so they want A, write an equation that gives the hailstone's diameter d after t minutes if you assume that the diameter varies directly with the time. So varies directly with the time. So remember that in our direct variation equation, y equals a times x, where a is a constant of variation, meaning that whatever number a is, when I find it, it's not going to change throughout the duration of the problem. So it varies directly. And when you have direct variation, what this means is that y varies with x. Varies. Assume that says varies. Varies with x. So what I'm going to do in the first part is just plug in the equation or the values of the equation, because it says y varies directly with x. So I plug in the values. So it says y varies directly with x, and they're saying here that the diameter varies directly with time, or we're assuming. So y is going to be d for diameter. A is my constant of variation, which is what I'm going to look for. And x in this case would be time, because it's saying that diameter varies directly with time. So that's pretty much the first part of the problem, where they want us to write the equation. And the first part of the problem, or part A, says basically the way you would write it is d for diameter varies directly with time times A. Now, the second part of it, of the problem, says that we're going to use this very equation that I'm boxing in, and they want us to predict the diameter of a hailstone after 20 minutes. So here's the problem with the diameter. If I look at the diagram, so if I look at the diagram here, the first one, I don't have a diameter, and all I have is 20 minutes. So there's really nothing I can do, because not only do I not have the diameter, but I don't have A. I don't have a constant of variation. So that means I have to find A in order to find the diameter here. So what do? Well, I look at my second diagram, and I know that I have the diameter of the other hailstone, which is 0.75 inches. And this hailstone of 0.75 inches forms after 12 minutes. So I can actually use this information here to find my A, and hence be able to find the diameter after 20 minutes, which is what I'm being asked to do. So all I'm going to do is just plug in and say, well, diameter right here, the diameter, instead of writing diameter, I'm going to write 0.75 is the diameter. A is what I'm going to look for. And A, remember that A represents a constant of variation, meaning that that number will remain constant throughout the problem. So T is 12. So now that I have my diameter and I have my time, I can simply divide, in this case, by 12, and I'm going to get my constant of variation, which is what I need to solve or to find the diameter after 20 minutes. So I divide by 12. This is going to cancel out here, right? A is going to cancel out. And that would be that A, in that case, is going to be 0.0625. However, I am going to do the division right here just to make sure that I am not making any mistake, and that's correct. So A is going to be 0.0625. 0.0625. Now what that's going to do is it's going to be my constant of variation. Now that I have my constant of variation, I can go here to this part, which is what I'm going to find now. Now I can find my diameter because I have my constant of variation. So what you're going to do now is say D, which is what I'm going to look for, equals A, which is 0.0625, and you're going to multiply it by the time, which is 20. So I found the constant of variation here, guys. I'm boxing it in so you guys know where I got that number from. And now I'm going to look for the diameter after 20 minutes because I have my constant of variation. So what I do now is I multiply D times, or 0.0625 times 20, and the answer is approximately 1.25. 25 inches. So that means that after 20 minutes, the hailstone now has a diameter of 1.25 inches. And ladies and gentlemen, that would be my answer for that example. Again, the first thing they want us to do is to find the equation assuming that diameter varies directly with time, which means that I would substitute the dy for d. A is pretty much a constant of variation, so that remains unchanged. And the x would now be time because it varies directly with time. So I have the next step is to find the diameter after 20 minutes. I don't have a constant of variation, so that means I cannot find the diameter after 20 minutes. But I do have at the bottom second diagram, I have the diameter of a hailstone after 12 minutes. And after 12 minutes, the hailstone has a diameter of 0.75 inches. So we plug in the numbers here. Okay, so again, we use this diagram and we plug in the 0.75 for the d, and we plug in the 12 for the t, and then we divide by 12 on both sides, and that equals 0.025625. Okay, so I got that from, because I'm trying to find the diameter to 20 minutes, but I don't have a constant of variation. So I use the information here to find my constant of variation. Once that's done, now I go back here and I can find my diameter. Diameter is what I'm looking for. I found my A, which is my constant of variation. And remember that it remains the same throughout. So 0.0625 times the time, which is 20, and that gives me 1.25 inches. So after 20 minutes, the diameter is 1.25 inches. Now, I'm going to go ahead and delete this and erase that. If you have any questions, you can pause and rewind the video. And I'm actually going to go to the second example, also on page 108, which would be the last example of the section, and it's another story problem. Now, before I get into the details of that story problem, there are some things that I want to discuss about using tables and applying direct variation to real-world data. Okay, so let me erase this so we can have some space. And I can erase this, and I can erase this, and I think the story problem here can be deleted as well. Okay, so now let's see if I can move this bar a little bit. There we go. And it says, great white sharks have triangular teeth. The table below gives the length of a side of a tooth and the body length. It says show the direct variation. If so, write an equation that relates to the quantity. So I want to know if there is a direct variation, and if so, by how much. So far we've seen direct variation being used in the form y equals a times x, where a is the constant of variation. But when we're working with tables and data, we have to find direct variation. But because we have the information reported to us differently, here we have in the first example we had diagrams. Here we have a table, and the information is reported differently. So that means that this equation has to be expressed differently in order to be able to use it here. So what we do is we rearrange the equation by solving for a specifically in this case, and we say that a, or the constant of variation, and that's only when we have information in the form of tables, is we say that the constant of variation is y over x. So we have the formula that says a equals y over x. Now, whenever we're working with, so that means that I have to basically, to find the constant of variation by how much there is a direct variation of, I have to divide whatever value y is by whatever value x is. So when we have tables, that can be kind of tricky to determine who's x and who's y. Remember that y is what we call the dependent variable and x is the independent variable. So if I look at the table, I realize that at 1.8, the body length is 219 centimeters. At 2.4 centimeters, the body length is 290 centimeters. At 2.9 centimeters, the body is 350 centimeters. At 3.6 centimeters, the body length is 430 centimeters. At 4.7 centimeters, the body length is 585. And at 5.8 centimeters, the body length is 695. So there is a relation. And as you can observe, the longer the body length, according to the table, the longer the teeth. So apparently there is a direct variation. There is a relationship between the length of the body and the length of the teeth, but we want to know if it's a direct variation. And what we do in that case is we divide. So because x, which in this case would be the length of the teeth, is affecting the results that I'm getting for the body length, we simply say or assume that in this case y would be the body length. So we would say b, and we know that x would be the t because it's the independent variable. And what I mean by the independent variable is that it's the variable that's causing the change. And we're going to look for A. So the way we do that is simply by dividing. Dividing to, in this case, B over T. So you would say 219 divided by 1.8, or 215, excuse me, not 219, 215. I realized that I made a mistake here. It looks like a 9 and it's actually supposed to be a 5. So let me fix that. This is not, this is 215. Let me just write it better because it didn't look like a 5. Okay, there you go. So 215 divided by 1.8, and that would be approximately 119. And then you divide 290 by 2.4, so 119. 290 by 2.4. Two 90 divided by 2.4 is 121 approximately. And now we're gonna look at 350 divided by 2.9. 350 divided by 2.9. And that is going to be approximately 121 as well. Then you have 430 divided by 4.6. And 430 divided by 4.6 is 119 approximately. Then you have 565 divided by 4.7. Now I did these answers, or I divided these problems using a calculator, and you see that some of them say equal and some of them say approximately, and that's basically because you're rounding. If you use the precise value, you'll see that these values are closer to 120 than they are to 119 or 121, except for the cases of 290 and 2.4. And let me do this real quick. And 695 and 5.8. Let me just do this and then I'll explain what I'm trying to say. $695 and 5.8 is approximately 120. So if we divide 350 and 2.9, we don't get an approximate sign. We get an equal sign. So this one is not rounded or anything like that. So that's why if you look in your book, it says equals. If you look, so basically, if we divide and when you have, let me get the spotlight real quick so I can explain something. So when you're working with a division and you have the approximate sign, which is kind of like a curved equal sign, that means that the answer was probably rounded off to the, in this case, to the nearest degree. So that's why if you look at 215 and 1.8, you have the approximate sign as well. Likewise, if you look at 290 divided by 2.4, you also have approximately 121. If you look at 350 divided by 2.9, it equals 121. So that means that there was no rounding there. And if you look at 565 by 4.7 and 695 by 5.8, if you look at those problems here, they're both approximated. So what you're doing is you're more or less, depending on what you've got, approximating. So if I look at 565 divided by 4.7, the problem is approximately 120.76. If I look at 470 by 4.6, if I divide that in the calculator, I mean 430, excuse me, 430 divided by 4.6 divided by 3.6, I get 119.44. Likewise, if I divide 290 by 290 divided by 2.4, your answer is 120.8. So you round that to 121. If you look at 215 divided by 1.8, and this is me getting the precise values, you get 119.44. So basically, if you look at your answers, the numbers that are 121, like for example 290 and 2.4 and 350 by 2.9. If you look at those numbers are 121, but the majority of them has a ratio between 119 and 120. So if you were to divide each one individually, if you were to divide this individually and this individually and this individually using a calculator, you would see that the answers are closer to 120 than they are to 121. And this is normal when you're using real world data, like measurements in the case of the great white sharks. In that case, you simply round your answer or choose the number that it's closest to. So in this case, we would say that A equals B over T, and that the formula is A equals B over T equals, give me 1 second, guys. It says, because the ratios are approximately equal, the data shows variation. An equation relating to tooth length and body length is B over T equals 120. So we would say in this case that B over T equals 120 because, again, when you divide the values, and again, I'm going to read from your book, it says, because the ratios are approximately equal. They're approximately equal, meaning that there is a variation, but there's not a whole lot of variation. It's not like the numbers are completely different. Like one is 120 and the other one is 150 and the other one is 19. That, in that case, shows no direct variation. Now, if I divide like I did there, like I did here, and the answers that I get are similar to each other, 119, 121, 119, 120, and 120, then I can say that there is a direct variation, and we use 120 because it's the number that they're all closest to. So that is pretty much how you determine direct variation. Again, if you have a table, you find the variation, and then you basically divide each column individually, and you get either the same number or close to the same result when you divide each column, and that represents a direct variation. So guys, hopefully this video helped. The LMS is already uploaded to College One, so stay safe and have an awesome day.